Okay, hi everybody. We're sitting now on the last chapter in the course for the semester on light and matter, and this is the third in a series of 3 lectures on light and matter. And this first slide you may remember, hopefully you watched it already, from the prior part 2 of this, summarizing the different types of spectra that we see. And just as a reminder, we talked about 3 different types of spectra. One is the continuous spectrum, which is shown right here on the bottom. And this is from a light source that's at some elevated temperature, and typically light bulbs, when they filaments glow, when voltages pass through them, they're fairly warm, and they create a multitude of wavelengths that all come out in terms of a continuum. When they pass through the prism, as you know, light slows down and refracts, and red refracts less or bends less than the blue. And therefore you can see that this type of a source contains many different wavelengths of the visible. We also reminded you of what's called an emission spectrum, and the emission spectrum is shown right here. And the emission spectrum is when a gas, a single element, not like a light bulb, but a single element, when it glows so much that if it glows, then it's visible and you can see it, and it travels through the prism, and lo and behold gives us a series of bright lines on a dark background. The dark background is just the background, and the bright lines are such that the distance or the spacing between them and the number of lines there is characteristic of each one of those elements. You can tell whatever element it is by its characteristic fingerprint, just like a barcode is in the supermarket. And finally, the third type of a spectrum that we discussed was this thing here called the absorption spectrum. And in the absorption spectrum, there's something absorbed, obviously. And what you see is, you see the continuous background right here with now dark lines superimposed. And what are those dark lines? Well, those dark lines are just the element that somehow got in the way of the light beam. The element got absorbed. And what's happening here is, notice the light source, the bulb, emits light, it goes through the gas, this cloud of gas, it gets absorbed, so you can see the continuum that the light bulb normally gave with these lines from the individual elements subtracted. And that's why you see these dark lines on a continuous background. That's called an absorption spectrum. And as I told you before, that's similar. The absorption spectrum is the spectrum of the sun, because the disk of the sun emits a continuous spectrum, and then as the light from the disk goes through the atmosphere and the gas surrounding the sun, that gets absorbed, and we can identify the elements in the sun's atmosphere that way. So the sun has a continuous absorption spectrum. All right, I want to talk about the last topic we're going to talk about today, and it's going to be on the Doppler effect. And I'm going to show you a series of videos, one after the other, on the Doppler effect. And what is the Doppler effect? And let me show you this first video, and hopefully you may recognize some of this, and we'll explain it. I want to show you a few different videos before I start explaining. So here we go. What I wanted you to notice there is not that, oh, gee, this is a nice looking train, but I wanted you to notice as the train approaches us, listen to the sound of the train. Listen to the pitch. The pitch is the frequency of the sound wave as the train is traveling towards us. And then as the train passes, listen to the change in the pitch or the change in the frequency. Let's listen to that again. probably heard that several times. You've heard that type of a rising in pitch and lowering in pitch. This is a demonstration of something we call the Doppler effect, which was named after I don't know if it was a Danish guy's name was Christian Doppler, and he had explained why this happens to sound waves or anything. Let's watch it now, not only with a train, but let's hear it with a car. And you may have also heard this a lot on the street, sometimes when ambulances go by or something. So let's hear the next one. Okay, did you hear that? Okay, I'll play it one more time. Notice as the car is beeping his horn as it's coming towards us, we are at rest. We're on the side of the road, and the moving car coming towards us is emitting sound waves, and we hear the frequency of the sound waves goes up as the car is approaching us, and as the car starts going right next to us and then going away, the waves get lower in pitch. This is an example of the Doppler effect. And you've probably heard this several times. You never realized what this was. So let's play it again. Yeah, hear that change in the pitch of those. Let me show you. So what the Doppler effect is a phenomenon where as waves approach you, they get bunched together. As they're coming towards you, the waves get squished. The wavelengths actually get smaller as they're coming towards you because they get bunched together. And then as the object passes you, the waves will stretch out. They'll get further apart. That's an example of the Doppler effect. Let me show you another video we call the Doppler effect Big Bang style.
Hey, Sheldon, there's something I want to talk to you about before we go to the party.
I don't care if anybody gets it. I'm going as the Doppler effect.
No, it's not.
If I have to, I can demonstrate. So what time does the costume parade start?
The parade?
Yeah, so the judges can give out the prizes for best costume. Most frightening, most authentic, most accurate visualization of a scientific principle.
Sheldon, I'm sorry, but there aren't going to be any parades or judges or prizes.
This party is just going to suck.
Oh, come on, it's going to be fun, and you all look great. I mean, look at you, Thor, and Peter Pan, that's so cute.
Actually, Penny, he's wrong.
Hi, Peter Pan!
And I got a handful of pixie dust with your name on it.
No, you don't. Hey, what's Sheldon supposed to be?
Oh, he's the Doppler effect.
Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Oh, sure, I see it now, the Doppler effect. All right, I got a shower. You guys, make yourselves comfortable.
Okay.
See? People get it.
Oh, hi.
Hi.
Hello.
So what are you supposed to be?
Me? I'll give you a hint. Meow.
A choo-choo train?
Close. Meow.
A brain-damaged choo-choo train?
I still don't get it.
I'm the Doppler effect.
What
Okay, if that is some sort of learning disability, I think it's very insensitive.
Why don't you just tell people you're a zebra?
Well, why don't you just tell people you're one of the 7 dwarves?
Because I'm Frodo.
Yes, well, I'm the Doppler Effect. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
So that's Big Bang Theory style. But the Doppler effect is exactly what Sheldon said. It's the apparent change in the frequency of the wave based on the source, the change in the frequency based on the position of the source and the observer. So if you're an observer sitting on the side of the road, and as the waves approach you and go away from you, they bunch up as they come close to you, and they stretch out as they go far apart from you. As they go further away from you, as the source of the waves is moving away from you. And this not only happens with sound waves, it also happens with light waves. And what I want to explain to you is here's the Doppler effect, okay? And here you can see there's a Doppler effect of sound waves. You can see here as a car is approaching you, the waves bunch together. Notice the waves are bunching together, and as the car is moving away from you, you can see here the waves spread further apart. And in sound, as the waves come close together, their frequency or their pitch goes up, it rises, and as something moves away from you and the waves stretch out, the pitch goes down, and the pitch gets lower. It goes more towards a bass tone, okay? And this also, okay, the Doppler effect is used pretty much in daily life, and hopefully you've never seen this guy on the side of the road coming towards you, but you can see it's a state trooper, and what he has is he has a radar gun there, and that radar gun uses the Doppler effect in order to measure your speed, okay? The highway patrolmen, they use that Doppler effect to measure the car speed. And, well, how does it work? Well, let's look at that. Okay, if you look right here, here is this little radar gun, and the officer is sighting through a little tube, and he's looking at your car. And as your car approaches him, this top little emitter here emits a radar wave or radio wave. That's a visible light wave. That's a light wave. Okay, that's a light wave. Okay, this is, I told you, the Doppler effect not only works for sound waves, but for light waves. And that's really the reason I'm talking about the Doppler effect today. Sound waves, you just hear them, you see them, and you hear that, you see that phenomenon occur often and hear it often, but it also occurs with light waves. But so as the officer here is sending out a radio wave, okay, towards your car, and the grill of the car will actually reflect the radio waves coming out. And the frequency of the radio waves is completely known as this emits those radio waves. Once it hits your car and bounces back, this bottom aperture right here, this bottom hole, is a receiver. And what the officer is doing, or what this device is actually doing, a little chip built into the device, is doing a calculation. It's measuring the frequency of the car coming towards you. Okay, so as the waves are emitted, and as the frequency, as the radar hits the front grille of the car and gets reflected back, he measures the frequency coming back. So he knows what frequency was sent out, and he knows what frequency is coming back. Okay, sorry for that interruption, but what happens is the officer is releasing radio waves. A radar gun is releasing radio waves from the top of a known frequency. They set the frequency of the radio waves as they come out, or the radar, and then they're measuring what comes back in at the bottom. So the radio waves going out, known frequency, when they bounce off the car, what's going to happen is as they're traveling back to you, they're going to get squished together, right? Because the car is approaching you, it squishes the waves together. So what this what this device does a calculation of the frequency that went out minus the frequency that came back. And it sees the difference in the frequency. And that difference in the frequency is related to the speed of the car. They can calculate the speed of the car. Now, typically, I'd put it up in equation and show you this, but I told you I won't do too much math here, so that's why I'm not going to. But all I have to tell you is that this little radar gun, the patrolman's radar gun, calculates your velocity, your speed. All right, and if it's over the limit, they can give you a ticket, something, and that's how they do it. So it's how your car reflects the radio waves back to that device. And there's no lying there. There's nothing you can do. It's also used, if you can see a little further down, this little radar gun is also used at baseball games. Here is one of the few photographs I was able to find, and you can see right here, somebody stands behind the pitcher and then has the radar gun right here, and the radar gun is shooting radio waves as the pitcher throws the ball. And as he throws the ball, what's happening is the radar waves are bouncing off the baseball, and they're being stretched because the baseball is moving away from it. And typically, this is not the way it's used in a baseball game. It's usually used behind home plate. If it's used behind home plate, what happens is the radar gun is aimed at the pitcher, and as he throws the baseball to you, the radio waves bounce off the baseball and get compressed. They go to a shorter wavelength. Okay, it goes to shorter wavelength. And that's how they determine the speed of the ball. Next time, if you ever happen to go to a stadium, take a look. There's usually one of these guns, and I think it's made by a company called Jugs, and it's called the Jugs gun. And this little gun is usually behind, on the screen behind the catcher, and it's pointed at the pitcher, and it measures the speed of every pitch. So these are typical devices. This is how the Doppler effect is used in everyday life. Okay, the patrolman uses a radar gun to measure the speed of a car, and in a baseball game they can use the same type of a radar gun to measure the speed of a pitch. So that's how typically this is implemented. The Doppler effect is implemented. So here it's being used to measure the speed of something. But the Doppler effect is really just the shifting in frequency of a wave. That's what it is. If the wave is approaching you, the shift goes to shorter wavelengths, higher frequency. As an object is moving away from you, it gets shifted to a lower frequency as the waves stretch out. And this not only happens with sound, it also happens with light. As I told you, here's the radar gun with light. And here's the video that I was telling you about last time. Here's another video kind of summarizing that. And as I told you, the gentleman has a little English accent. It may be a little difficult to understand, but let's see if we can hear it right now.
The Doppler Effect. In Sheldon's words,
It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
the Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and a car drives past you very fast. As it does so, it honks its horn, because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look out your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does it mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence for the Big Bang and an indication that the Earth might get very lonely in the distant future. Thanks for watching this video. Let me know if you got something out of it. Bye.
So, what's interesting is this same effect occurs with light waves. As a light wave approaches you, okay, depending on what its source is, it's a source of light waves like a star. If, as a gentleman said, as the star is approaching you, the light waves from that star get bunched up together. And there's a slight change in frequency, right? As the waves are approaching you, the frequency is bunching up together. The wavelengths are bunching up. The wavelengths are getting shorter. It's going to higher frequency. So the color of the light changes just a little. You can't see really, hardly detectable, but it changes just a little, okay? And when a frequency is increasing, we say it's going towards the blue end of the spectrum. In the visible part, when we're talking about light waves, we're talking about the visible portion of the spectrum. As the waves approach us, they move towards the blue because that's higher frequency. Also, but if the star is now receding from us, is moving away from us, the waves get stretched out. They go to lower frequency. And lower frequency light waves are more red. So if they're a little red, they'll get even a little darker red. Not by very much, something that probably we would not notice, but certainly can be measured. And here's a picture. As you can see right here, we have a little diagram showing here's the bunching up of waves as they approach you, and that's called a blue shift as they get closer and closer together. And if something is receding from you, a source of light waves is receding from you, the waves get stretched out and go to a lower frequency, hence a redshift. And one of the things the reason we went over this is because what we're going to see is, as astronomers are looking out into space, almost everything that they look at is only redshifted. There are very few things that are blue shifted. Maybe some nearby objects. By nearby objects, I mean other galaxies. Like the Andromeda galaxy is blue shifted a little because it's moving towards us. The waves are bunching together. But every other galaxy, okay, is all redshifted, meaning everything is flying away from one another. And that was the evidence for the Big Bang, because they saw that everything is moving away. What is it? The universe is expanding and everything is moving away from us, like we talked about before, like this expanding balloon model when we had dots on the balloon. All the other galaxies are moving away from it, and because we can see it by identifying this redshift. If you look here, down below, this diagram right here represents the emission spectrum. Remember when we talked about the three different types of spectra? We talked about emission spectra, and this is an emission spectrum of hydrogen. And there are three spectra here. One for hydrogen moving away from us, receding, one for hydrogen approaching us, and the one right in the middle is for hydrogen at rest. And we can see this is emission spectrum. Hydrogen, a pure element, has a barcode, has this emission line spectrum. And it has a line right here, a red line. It has another teal colored line here, and more bluish and more purple as you go here. Those are the characteristic lines signifying the presence of hydrogen. And notice that they occur at specific wavelengths. These are the wavelengths of this red line is at 656.3 nanometers. A nanometer is a billionth of a meter. Light waves are very short wavelengths. So the red is the longest, 656, and as you move towards the blue, it goes into the 400s and 300s. So you go from 600 or 700 close to 300. That's from red to blue. And notice here, the wavelengths get shorter. 486, this one here, 434. So this is for a hydrogen. This is for an element hydrogen, let's say in a star, if the star is not moving towards us or if it's not moving away from us. Let's say now the star is moving towards us, okay? And then we look at this one right here, the approach. It's approaching at a velocity of 600 kilometers per second. I just picked a number to show how much the shift is. Look now, this line of hydrogen, instead of being at 656.3, has now gone a little shorter. It's gone to 655. It's actually, the wavelength has changed just a little. And the wavelength has gotten shorter. Why has it gotten shorter? Because the object is moving towards us, the waves are bunching up together, hence the wavelength gets a little shorter. And notice all of these wavelengths get a little shorter. 486 compared to 485, 434 compared to 433. These wavelengths are getting shorter. So notice the shift. It shifted from here to here. This small amount of shift here is a blue shift. Okay, that's from the object approaching us. And for the emission line spectrum on top, an object now is receding from us. That is, it's moving away from us. So instead of getting shifted towards the blue, it's going to get shifted towards the red. It's going to go to lower frequency. And you can see here, higher and the wavelength is now going to be longer. So we go from here, here's an object moving, here's the hydrogen alpha line when it's moving away from us. Notice this small difference here. It went from 656 up to 657. It changed. Okay, it increased a little. That's because the object is moving away from us. The wavelength stretched out, and you can see all the corresponding lines. So take a look at this now. If you can analyze the light coming from a distant object in space, you can first tell what the object is, what it's made out of because of these characteristic lines, whether they're emission lines or absorption lines or whatever they are. But you can also tell how the object is moving. If it's moving towards us, we'll see that the waves are approaching us. The waves will get shorter. And as an object is moving away from us, it gets redder. And as I told you before, 95% of the objects in the universe are all moving away from us. The universe is expanding. It's redshift. It's becoming redshifted. And as I told you, this is evidence for the Big Bang, the sudden expansion of the universe. And the universe is continuing to expand. So this Doppler effect is this changing of the frequency of a wave based on the source of the wave and the observer. That's what redshift is. So that kind of finishes the chapter for us. Okay, the things that we talked about here were, what is a wave? Okay, a wave has a period, that is how long it takes to complete one wavelength. A wavelength is just the distance between the same points on a wave, okay, whether it's from peak to peak or from trough to trough or whatever. The amplitude of the wave is how big the disturbance is. Then we also talked about special types of wave that are created called electromagnetic waves. And we said electromagnetic waves are caused by charges that are accelerating. Okay, these charges, where are they located? They're located inside an atom. There's electrons and there's protons. These have charges. Electrons have negative charge. Protons have positive charge. P, proton, positive. Electron, remember, is negative. But as these charges move and they accelerate, they create an electric field. A moving electric field creates a magnetic field, and a moving magnetic field creates an electric. So the electromagnetic waves are produced. And the more they move, okay, depending on the temperature is the big driver, they create the temperature is what creates waves. And what we said is that if a temperature of a body is at absolute zero, and that's right around minus 450 degrees Fahrenheit below our existing zero, absolute zero, that's when molecular or atomic motion ceases, okay, at that cold temperature. But nothing we know is at that temperature. Okay, so we also learned that all the waves, if we looked at the complete selection of every wave that can be produced, okay, it goes from the radio all the way up to the gamma rays, and there's a small portion called the visible, and those are the ones our eyes are sensitive to. So visible spectrum is the different wavelengths of light, the red, orange, yellow, green, blue, violet. That is the visible spectrum, the wavelengths of the visible spectrum. Okay. We can also tell the temperature of a body by measuring its black body radiation. Remember, we talked about those curves. As an object gets hotter, it emits a broader range of wavelengths, and the peak of that wavelength moves to shorter and shorter wavelengths. And as an object is colder, it's less excited and less waves come from it because the atoms are not moving as much. Temperature is not accelerating them that much. We also learned about a spectroscope and how a spectroscope takes light in, visible light mostly, and passes it through a piece of glass where the light slows down inside the glass. And as the light slows down, it refracts, it bends, red being bent the least, blue being bent the most, and we get three different types of spectra. Okay, we get a continuous spectrum, and that's emitted by a solid, or a liquid, or a dense gas. A gas that's something that's glowing at temperature. It's glowing. It's visible. Once it's glowing, it's visible. It's just like sticking a hot poker into a fire. Okay, once it glows, it's visible, and we can take that light and analyze it, and that'll give us a continuous spectrum. If we have a single element of a gas, and we heat it up, it's going to emit what we call an emission spectrum, characteristic lines, just like the barcode in the supermarket. Okay, each element has its own characteristic lines, and if a gas is consisting of a few different elements, all of those different elements are going to put in all different lines, and if we can identify them, then we can identify what the object is. And then finally, there's the absorption type of spectrum, which is a continuous spectrum with these dark lines in it. And those dark lines are really the same as the emission lines. And those dark lines match up with the emission lines, which is just showing you that somewhere between what produced the continuous spectrum and that light passed through a gas and was absorbed and was taken away. That's why it looks black. It's missing. That's what's called that continuous absorption spectrum. And finally, we learned about the Doppler effect. And the Doppler effect really measures the frequency of a wave. And we say the frequency of a wave changes is if the source of the wave is approaching you, the waves get bunched together, move to higher frequency or a shorter wavelength. And as the waves move further away from you, if the source is moving away, the waves get stretched, and that's the Doppler effect. And we see the use of the Doppler effect every day. Okay, when we hear, sometimes we hear in sound waves, we hear the sounds of ambulances coming towards us and moving away from us. But we also know that there are instruments that can also use the Doppler effect to the ability that they can measure the speed of a car, like a patrolman measuring the speed of a car with a radar gun, or as a baseball official measuring the speed of a pitch. Those devices are used to measure the velocity. They're taking the frequency of the wave, doing a calculation, and measuring the speed. And remember that the Doppler effect depends on the relative speed of the source and the observer. They occur with sound waves, and it occurs with light waves. Both sound and light both exhibit a Doppler effect, all types of waves. And in sound, when the frequency changes, we call it pitch. As the frequency increases, the pitch goes higher. When the frequency increases with light, it moves towards the blue, we say it's blue shifted. Okay? And if it's receding from us or moving away, it's red shifted. A good way to remember it is red shifted receding, RR, right? Red means receding, moving away. Blue is approaching you, and the frequencies get higher. So that's the summary for this chapter on light and matter.